Welcome to example number 5. We have the planet Mercury that is orbiting around the Sun in an ellipse. You're given a couple distances. You're given the distance at perihelion, which is the closest distance, and that's 4.6 to the power of 7 kilometers. And we're also told the orbital speed of 59 kilometers per second. At aphelion, the furthest point, we're told the distance, but we're asked to find out how fast it's traveling at this particular position. So we will make a few assumptions. We are going to ignore the small gravitational forces exerted by other planets on Mercury. We're only going to consider the force acting on Mercury, and that is due to the Sun. Gravity is a conservative force, so we know that the mechanical energy must be constant. If you look at the sketch of the orbit, you'll notice a few things. At the furthest point at aphelion, the Mercury is furthest from the Sun, and so its potential energy is the greatest at this point. And at that point, the kinetic energy will be the least. So we know that the kinetic energy, since it's at the least at aphelion, then it must have a velocity that is slower here than it is at this spot, perihelion. So let's label the given information. We are given a couple things here. We're given the velocity at perihelion right here is 5.9 times 10 to the power of 3 meters per second. I'm converting this from kilometers per second to meters per second because our gravitational constant is in meters and kilograms and seconds. We're also given the distance RP, which we need to convert that as well into meters, is 4.6 times 10 to the power of 10 meters. And we're also given the distance at aphelion, which is 6.98 times 10 to the power of 10 meters. There are a few other things that we also need to know. G, which is the gravitational constant, is 6.67 to the power of negative 11 Newton meters squared all over kilograms squared. And the mass of the Sun is 1.99 times 10 to the power of 30 kilograms. We are not given the mass of Mercury, but you'll find out that we don't need to know that because later on it'll cancel out. So we're looking to find the velocity at aphelion. So how are we going to approach that? Well, we go back to that assumption that the mechanical energy is constant. So since that's constant, we could say the sum of those two energies that make up the mechanical energy, that would be the kinetic energy at perihelion plus the potential energy at perihelion, is equal to the kinetic energy at aphelion plus the potential energy at aphelion. The kinetic energy at aphelion is 1/2 times the mass of Mercury times the velocity at perihelion. The kinetic energy at aphelion is going to be the same expression, except we're going to have the velocity at aphelion squared. Plus, we have the gravitational potential energy, which is negative g mass of the Sun times the mass of Mercury all over the radius of orbit at that particular point, which is rp. And then we have plus also the same formula here, but except now it's the other radius at aphelion. You'll notice that the mass of Mercury is in every term, so it cancels out. And if we rearrange the equation for the velocity at aphelion squared, we'll get the following expression: 1/2 velocity at perihelion squared plus we have the negative g m of the Sun divided by r at perihelion, and then we have also minus the other expression, negative g mass of the Sun at radius of aphelion. If you rearrange the expression, you will get the following: v at aphelion is the square root of the velocity at perihelion squared plus 2gm, and then 1 over r at a minus 1 all over r at p. And now simply you can substitute your numbers in, which should yield this answer of 39,000 meters per second, which simplifies to 39 kilometers per second. So you'll notice that I could do it any position, by the way. I can put the object at position here, number 2, and find the velocity at that point. It doesn't necessarily have to be at the furthest and the closest points. As long as you have some information at one point, the velocity and the distance, and then the distance at another point, then you can find the velocity at that particular point too. And that's it for this example.